Hello, I'm David. I'm the coordinator of the Maths Learning Centre. It's semester 1, 2021, and this is a revision seminar for statics. The official name of the course is Engineering Mechanics, statics. And I've been asked to talk about fluid pressure and bending moments, etc. And several people have very helpfully sent me the course notes and a few specific problems that they've seen in the course that they are interested in me figuring out. And I also have a textbook here which has very similar stuff from your notes. In fact, someone sent me a problem which was in the slides, and it was this exact problem from the textbook. So if you ever want to get access to this, there are a few copies in the library, and there's one in the Maths Learning Centre if you want to borrow it while you're in the Maths Learning Centre. Please don't take it from the room because they tend not to come. People tend to forget to bring things back or not forget, and they don't bring things back. If you're ever interested, have a look, but this seems to be where they get a lot of their problems from. So, yeah. So I'm going to start with the fluid pressure problem. It's just going to be easier for me to work through problems than to talk about the general idea, but I will try and talk about what I've seen in the notes. Okay. Right. So since the one in the textbook is the same as the one in the notes, I'm just going to do the one in the notes because it's the one that matches most closely. So this problem gives a picture of a big slab of concrete that is not flat on the right-hand side of the picture, and a big bit of seawater on the left-hand side of the picture. It's given me a formula for what the equation of the graph is based on the location of the x and y axes at that spot. And it's told me rho is 1,000 kilograms per meter cubed. I'm presuming that's the density of the water. And it wants the magnitude of the resultant hydrostatic force acting per meter length of the wall. Okay. So I think there's some assumptions here. When it says per meter length of the wall, I think it's saying that actually this, I'm just going to draw this picture on my piece of paper. So my picture goes, there's the water, there's y, there's x, there's a parabola, damn it, there's the floor, that's 1 meter, that's 4 meters, and this curve is y equals minus 4x squared, and there's concrete here, and this is water. Okay. And the density of the water was 1,000 kilograms per meter cubed. All right. So that's the picture. And I think when it said per meter of the wall, the idea is that this is actually like here, and then it goes forwards and back like this to produce like a big wall that's like this shape going inwards, and then there's water here. That's what it's doing. So coming toward the wall, I imagine, is coming towards me and going inwards, and I want to know what the pressure is per meter of wall. Okay, right. So let me see if I've got some things right here. There's a formula for how to figure out the pressure of the wall, pressure of the water on anything that is in the water. And that formula is somewhere nearby here. And actually, I should get it from your notes. Does anyone remember what it is off the top of their head rather than having to look it up? Rho GH. Awesome. That sounds reasonable. Oh, there it is there, Rho GH. Gotcha. What symbol do they use for pressure? P? All right. Where this H is the depth, and that's the density, and that's acceleration due to gravity, like a 9.8 thing. Okay. And so that's telling me that every depth, there'll be a different pressure. And there'll be no pressure here when the depth is 0, and the pressure will get bigger and bigger and bigger until down here it's the biggest pressure that we can get. Okay, cool. And then the G is always the same, the rho is always the same, so that's all fine. It's all based on the H. And then pressure is newtons per meter squared, right? Okay, cool. So to get a force, I have to multiply the pressure by the area, and that will produce a force. But to get a force per meter, I could, just a second. So force equals pressure times area, because this is in newtons per meter squared and this is in meter squared, and that'll produce just newtons. Okay, but force per meter would be pressure times length, because that will be in newtons per meter squared and that will be in meters, and so I'll end up with newtons per meter. Okay, so I don't need to figure it out per area and then divide by how long the thing is, because I can just do it per meter straight up. Does your lecturer do it that way? Or does he figure out the area first? Or does he just call the length 1 or something? There's two options there. Just calls the length 1. Okay, that might make more sense. Okay, I'm going to do it that way then. All right, so my understanding of this is that this is a bit tricky. So I know that the pressure at this depth, the pressure is the same everywhere, and it's technically pointing inwards on this thing. And so if I needed to figure out what the pressure was doing, I'd actually technically have all these slanting arrows that would need to be combined together somehow. But there's this really cool trick you can do where you can say, well, that's okay. The vertical piece will be caused by the weight of this water, and the horizontal piece will be caused by the pressure. That's the magic trick that we use, so we don't have to actually figure out pressures pointing in slanted directions. So this water here has a weight, and there's pressures pointing inwards here, getting more and more and more until we get down here, like that. And these can be turned into a force somewhere in the middle there, and this can be turned into a force pushing down, and the force pushing across and the force pushing down together will produce a magnitude of the total amount of force. That's the plan. How are people feeling about this so far? Cool. All right. So one piece at a time. Let me deal with the weight of the water. Oh. Oh, that's okay. Cool. All right. So, well, this water would have a certain amount of volume, and then if I multiply that volume by the density, it ought to give me a mass. And then if I multiply the mass by the gravity, it should give me a force. That's my plan. And to figure out an area, when I've got a formula for things, I would need to do an integral. Unless I had a formula for the area of a parabola, which I don't think we have, though it does exist, I'm going to have to do just the integral. So this area here, at every x position here, will be that length, and all those lengths accumulate and stack together to produce an area. So I'm thinking that I'm going to have that this area here is the integral from -1 to 0, because that's the coordinate system I've been given, times the distance. So the whole height here would be 4, but then I'd be taking off, no, it won't be, don't worry. This height here is 4x squared. Like it's minus 4x squared because it's pointing downwards, but I can do that. And so since I want to count this as a positive length, I'm going to make it a plus 4x squared. And so let's see, the 4 is multiplied on, so it will still be multiplied on afterwards. The x squared will go up to x cubed, and I'll have to divide by the new power. And then I'll have 4 times a third times 0 cubed minus 4 times a third times minus 1 cubed. And minus 1 cubed is -1, and -1 times -1 is 1. And so I get 4/3 meters squared for that area. How was that? Sweet. I really feel like saying this now. It's probably not very relevant, but it's a fun fact. A parabola, the area of any shape of a parabola is 1 of this depth times 1 of this depth times, so 1 of this depth plus 1 of this depth plus 4 of the depth in the middle divided by 6 times the width, and it'll come out to the correct answer. So there you go. So I've got 4 of this. So 1 of this is 4, 1 of this, I'd need to know the depth in the middle, which is sad, but I could figure out this whole area here, and so that'll be 4 plus 4 plus, but that'll be the area underneath the parabola, not the area on the outside, so I'd have to subtract it, so no point doing that. But anyway, that's just a fun fact about parabolas. Okay, so that's the area here. It's 4/3 of a meter squared, which means that the volume of water is 4/3 times 1 meter outwards. So I'm just going to assume that it's 1 meter long. So since I'm doing it per meter, I should probably say this here, this was 1 meter long. And so it's still 4/3 meters cubed, which means that the mass will be 4/3 times 1,000, because it's 1,000 kilograms per meter cubed. And that means that the weight will be 4/3 times 1,000 times the value of, is it 9.8 or 9.81? Okay, cool. Different courses use different answers for that, so I just wanted to check. So whatever this answer is, that's the weight. Should have brought a calculator. Oh, cool. 9.81 is a multiple of 3. Sorry. Works out to a nice whole number. That many newtons. Okay. So I've figured out that the weight of the water pushing down on this is 1.8 newtons. Oh, sorry, no, 13,018 newtons. If I'm considering it being 1 meter deep in terms of my 1 meter wide, long in my picture. So that's one piece of this picture. I've got the weight here, and then I need to figure out what this is doing. All right, so these pressures, when they're multiplied by an area, will produce a force. So I know that the pressure here is 0 because it's at the top, and the pressure here will be, what did you say it was? Rho g h, and the depth is 4 at this spot. So whatever that is, I can figure it out. Okay. And so I can try and combine all of these pressures along this entire thing into one pressure. So if I have pressures going this way, and these arrows represent newtons per meter squared, times a distance in meters, that should produce newtons per meter when I go these lengths times this length as an area. So the area here will be measured in newtons per meter squared this way times meters this way, which will produce newtons per meter total. And so if I can figure out the area of this triangle and multiply it by the length, it should produce a total number of newtons then. Okay, so the area of the triangle, I'm just putting inverted commas because it's an area on my page, but it's not an area in the real world. So it's 4 meters, it's 39240 at the bottom, times the height, which is 4, and the area of a triangle is half of the base times the height. And it's a right angled triangle, so this is the base and this is the height, so that's fine. And so now we have that the total pressure per meter newtons per meter. And so therefore the total force should be times 1 because it's 1 meter long. I'm sure you could do this faster without writing down a lot of this stuff and go straight to the force is equal to this area times 1 and do it all in one calculation. I have trouble doing that. But if you've got more practice at this than I have, then you might be able to do it faster than I did. I'm hoping that me going slower makes it easier to see all the things that happened though. Okay, so now I'm going to redraw my picture on a whole new page because, you know. So now what I have is that this force is pushing downwards. This weight of the water, I shall call it W, and that was 13080 newtons. And there's also a horizontal force pushing this way, which I shall just call F. And this F was, we just figured that one out then, 78480 newtons. Cool. Now I could, if I wanted to, figure out the exact location of this force and this force. This one would have to be acting at the centroid of that water, and this would be acting at the centroid of this triangle. But I'm just going to check if I really need to do that, because the centroid of a triangle I can deal with. It's always 1/3 of the way up from the base, so that's fine. I can do that one. But the centroid of a parabolic minus bit, I'm not sure. But I don't think I need it, because they want the magnitude of the pressure of the force, and I don't need to know where these are to be able to combine them as vectors. And so the total force, as a diagram, it has this one pushing down and this one pushing this way. And the total force is there. That's how you combine forces together. And so Pythagoras' theorem will do the trick. So the magnitude which will be whatever it is, horrifyingly large numbers. One 3,080 squared plus 78480 squared, and then the square root, oh damn it. Seven, 9, which is approximately to a couple of significant figures. I don't know how many decimal places you're supposed to do. Maybe I'll do 796. Or just leave it like that. I'll just leave it like that. Do they have an idea? Do they have a convention for how many significant figures you're supposed to do? All right, how are people feeling about what happened there? Oh, sorry, Danny, I missed that. Missed some questions there. I'll just come back. So I didn't put a minus here because I want to figure out the literal, physical, actual area of the actual water that's in this spot. And so I don't want the answer to come out to be a negative answer, which was the correct thing that you said, Danny. And so I looked at, when I was at this spot, this literal distance is just 4x squared. The minus 4x squared tells you the coordinates of this spot, but I want the literal distance to figure out the area. Okay. Well, I'm not sure if I'm doing this right, but I think this is correct to do it Pythagorasly, because these forces are pointing in different directions, so the way they combine won't be straight up adding them together. Yeah. And it's to do is with the fact that they're pointing in different directions. If one of them was pointing at slant ways, then I'd have to use like the cos rule or something to do it. Okay. There were some really good questions in the Zoom. Anyone in the face-to-face room got thoughts or questions about this? Cool. All right. So That's pretty much what I could find in your notes about fluid pressure. That's all encapsulated in this one problem, and I don't think we need to do anything else. Would you like me to do a different fluid pressure problem before I move on to something else? Yeah, do another one. Yep. Got one in mind, or do you want me to just pull one out of the book? What's that? Okay. Just give me a moment. I'm going to pause the recording while I find one. Okay, this one says, determine the magnitude and the location of the resultant hydrostatic force on the submerged rectangular plate here. And the density of the water is 1,000 kilograms per meter cubed. So the picture here is saying, here we are underwater, and there's a wall under the water here, and the plate is underwater and it's 1.5 meters wide and 3 meters high. But then from the side view, this is what the concrete looks like, and it's 2 meters down from the water level and then 3 meters down to the bottom of the plate. Okay. Right. So it's this view that's going to be the most helpful for actually doing the problem. This one just tells me how wide the plate is. So in the other one, the wall was really long, and I wanted to know what it was per meter. I'm struggling with the people in the back couple of rows. Just that being able to concentrate on two things at once is hard. In the other one, I just chose that the length was 1, but I've been told the length is 1.5 in this problem, so I'm going to have to use that number. Okay. So I'm going to redraw my picture. There's the water, there's the concrete. Here's the actual rectangular plate that's in the wall there. So if I look at what the pressure is doing inside the water here, at this point there's no pressure, and at this point down here there'll be a certain amount of pressure, and it will go like this, like that. But only the bit that's actually on the wall itself is the bit that I'm interested in. Like that. And so it's that amount of pressure that's pushing on the plate that I'm going to need to somehow combine together into one force. If I just combine this drawing, it'll be in forces per meter, newtons per meter, and I'll have to multiply it by the depth, this length here, to get the per just straight up force. Okay. So this is a trapezium. So I could, if I wanted to, literally figure out the formula for what these lengths are as something involving h, and do an integral to find the centroid if I wanted to, in order to calculate what the location of this is going to be, because the location is going to be at the centroid of this shape. And that centroid, if it was a triangle, it'd be a third the way up the triangle, but the top bit's off, so it's going to be a little bit lower. So as far as I'm aware, the trick that most people use is they cut this into 2 pieces this way, so that there's a rectangle here, and I know where the centroid of a rectangle is, and there's a triangle here, and I know where the centroid of a triangle is. And so I can turn this pressure into 2 forces and then combine those 2 forces together afterwards. Okay, so that's what I'm going to do. So that's going to require me to figure out what the pressure is here and what the pressure is here. So the pressure here will be rho G times 2 because it's 2 meters deep. And the pressure here will be rho G times 5 because it's 5 meters deep to get to that spot. It's very easy to put the 3 in this spot because it's the other number that's in the drawing, but you need the total distance all the way down to this spot in order to get the right answer. That's one of the things I got wrong when I first did these problems with people in the Maths Learning Centre 13 years ago. Just pulled a number out and I couldn't tell what the problem was. So, yeah. Okay. Cool. Can I just leave it as rho G and deal with it later? Yeah, let's do that. I don't care to figure out what that number is. So I have two pieces. I have this rectangle, which was 3 meters high, and this was 2 times rho G here. And because I chopped it off, chopped this arrow into 2 pieces, this is 2 times rho G here as well. And so the total pressure per meter will be the area of this, which is 2 rho G here times 3 meters there. So that's 6 rho G newtons per meter. And the location will be halfway up this rectangle. There, because the location will be at the centroid of the rectangle. All right, I'll figure out where that is at the moment in a minute because I'll draw a new diagram. All right, this triangle, this was 2 rho G and this was 5 rho G, which means it's a very badly drawn triangle because this bit's actually longer than this. So there's 2 rho G here and 5 rho G here, which leaves that for this bit, it's 3 rho G left because it's 5 minus the 2 that we took off. And this is 3 meters as well. So the total pressure per meter is 3 rho G times 3. And the location, 1/3 the way up the triangle. Sorry? Yes, half. Yes, that would be a rectangle, wouldn't it? Whoa, good move. Thank you for listening for a maths mistake, interrupt, thank you. So that's 4.5, right? Okay. And it's 1/3 the way up the triangle. Whew, I did the area of a rectangle, didn't I? Wasn't paying attention. Okay. So these two pressure per meters, sorry, it's not pressure per meter, it's total force per meter, isn't it? These two force per meters can be now combined together into one force per meter. Since they're pointing in the same direction, I can just add them to get the total. But because they're in different locations and because they're worth different amounts, I'm going to have to do a centroidy thing to figure out where the actual location is. So that's why I'm just going to draw a brand new picture. So my brand new picture is this. There's 2, there's 3. I have one force that's halfway down, and that one was 6 rho G. And I have another force that was a third the way up, and that was 4.5 rho G. They're the two forces that I had. I choose to call them F rectangle and F triangle, if that's okay. They're not really forces, but it's close enough. No, let's make them forces. Yeah. Total force per meter, which means the total force must be force per meter times the number of meters, which was 1.5, because that's how deep it was, remember? 1.5 long. Damn it. I don't want to do 1.5 times 4.5. 1.5 times 4 is 6. 1.5 times a half would be 3/4. But I would, this is what calculators are for. Yes, okay. All right, I just thought I'd make them forces straight away, because then I don't have to do it later. It might have been a bad move, who knows? There's the water. So we've got one here, which is 9 rho g, and one here, which is 6.75 rho g. Okay. All right. So the total force, these two arrows are pointing in the same direction. I can just add them. And then that would be 15.75 times 1,000 times 9.81, which is whatever it is. How are we feeling? Oh, the chat. Cool. So the location, I'm going to have to somehow average out these two locations. And if you don't mind, I'm actually going to draw on this. This is 1.5 meters down, and this was 1 meter up, because the total was 3 meters. And the triangle was 1/3 the way up from the bottom, and the rectangle was halfway. So maybe what I should do is do them both from the bottom. Damn it. Because then I can average those two based on the fact that these are where they are. It was 3. No, 1.5. Just let me check. Yes, 1.5. I'll answer that in a second. So how would this apply if you had a slanted gate? Well, that's a good what if question. I love it, but I want to finish this one first. So that's the magnitude of the total force. They did also ask the location, and I've got 9 at location 1.5 up and 6.5 at location 1 up. I could actually just do the literal location from the top of the water. I think that's probably what they want. But they didn't specify how to tell them the location, so I'm going to say from the bottom of the gate as my location. So I've got 9 rho g newtons at a distance of 1.5 up. I've got 6.75 newtons at a distance of 1 up. And when I average those two across the total amount of newtons, that should give me the location. Yeah, which is how centroids work, right? This one was essentially the area of the rectangle. This one's essentially the area of the triangle. And you should be the area times centroid plus area times centroid divided by total area. That's where the centroid is. But also I'm literally just averaging out the location of all of the individual newtons. And so I'm going, well, this is where this location is. This is how many newtons have this location. This is how many newtons have this location. So this is the total locations divided by the total newtons should give me the average location. The rho g's will cancel, which is kind of nice. I already figured this one out. It was 15.75. That many meters from the bottom of the gate. I mean, it has to be between the 1 meter and the 1.5 meters because I averaged some things to get it. And it has to be closer to the 1.5 than it is to the 1 because the bigger force is at the top. And so that makes logical sense. You could have, if you wanted to, said it's this many meters from the water level, in which case you would have used the numbers to 4 meters and 3.5 meters. And you could have done that same thing and figured out the average distance from the top of the water, and that would have been fine. But since they didn't specify how, you can just, as long as you're clear about exactly where it's measured from, you can use whichever number you want. Right. So before I answer your what if question, anyone got any thoughts about what's going on here? Okay, so I've got one question. Why did I multiply by 1.5? Do you remember back in the other one I multiplied by 1 because it was 1 meter long into the page? This is the original diagram for this object against the wall of the thing. It's 1.5 meters long. It's 3 meters deep and 1.5 meters long. I can't see that 1.5 meters in this diagram. And so it's 1.5 meters deep into the page, always. And so I keep having to multiply that by that 1.5 because that's how long it is. And I need an extra times length to get an area. Okay. So, your what if question, love what if questions. This is how we learn, by asking what if questions. So you're saying, what if we had something like this and the gate was here? Something like that? Is that what you're talking about? Sweet. Okay, cool. Right. This is fine. This is, says the burning dog, right, in the meme. This is fine. We can do exactly what we did for both of these and combine them together. There is a certain amount of water sitting on top of this here. And there is also a certain amount of pressure pushing sideways on it. And those two things are what I'm going to have to combine to figure out the total force. So this area would have to be figured out as a literal area and then times by the length inwards, and that would produce a volume. Yep.
So this was the exact same rectangle as the question we just did. Could we take the pressure from the side we got and just add the height from the top?
Yes, you totally could. That is an awesome thing. So if this was 2 down to here, and this was 3 here, just making sure, well, I understand what your thing was saying. If this was 2 down here and 3 here, not 2 measured slantways, that would be different. You'd need to do trigonometry based on the angle to figure out the actual depth. But if it was 2 down to here and 3 down to here, this bit would be exactly the same as what we just figured out. Yes, awesome. And so I could replace this with that single force that I just calculated, or if I like, just use 2 of them. Yep. Yes, no, it doesn't matter. Yep.
If you were to combine these 2 forces, the horizontal and vertical, it would come out to a force which has an angle that is not parallel to it, right?
Yep.
And would you have to then find the vertical force in the plane of the plate and then find the direction forces of that?
So you're saying this would produce an arrow that's pointing some direction. Just a second. So when you combine these all together, you're telling me that there's a force. It might combine to be a force like this, yeah? And that's not technically pushing inwards on the plate like I would have expected. That's what you're saying?
Yeah.
I think the answer is, nah, just leave it as it is. Because the total... No, crap. No, yep. No, just give me a minute. I'm just processing. Because each of the forces the little forces that are here, if I just thought about so if I just thought about the hydrostatic pressure at each individual location, they would all be pointing in this way, right? And so that would produce, guaranteed to produce something this way. That's what you're saying, right? The total amount of force of the water pushing on this should be inwards on its thing. I think that the force that you get when you combine them is guaranteed to point in the correct direction. No, even if you, and if it doesn't, then you've done it wrong. That's my instinct. Sorry? Actually do the calculation. Sure. I'm going to try, damn it. Okay. Okay. All right, let's do it. We just figured out what this was, and this one was replaced with a force. This one was replaced with a force that was this much at this height from the bottom of the gate. The orange bit was replaced with that. So we can deal with that bit. And then the green bit, okay. Means this is 5 here. So it's 2 here and 3 here, which means that's 5 there. And so I have a trapezium that is however wide this is, which I don't know what that is. I shall call this distance L, if that's okay. I wasn't told what that distance was acrossways, so I'm just going to give it a letter. And so the area here, this is a trapezium. A trapezium is the average depth times the width. So the 2 parallel bits, you add them together and divide by 2, and you times by the height, but in that case it's the length in ours. Okay. And so the total, well, the actual diagram we've got is that this is now, we don't have that, damn it, just a second. That's the area. And then the volume will be that times the 1.5, because that's how long the gate is. 1.5 times 3 is 4.5, and 1.5 times a half is 3/4. So 5.25 times L. That L is not a litres, it's a length. Just so that many meters cubed. And so therefore the weight is 5.25 L times G, newtons. So I now have this bit pushing down, which is 5.25 G, and this bit pushing sideways, which was no, crap, haven't times by the rho yet. The mass times by the density, and now that's in kilograms. Oh, cool, they're both in terms of rho G. How cool is that? Nice. This was 15.75 rho G. And so the magnitude ought to be that. Now those rho G's will be able to come out of the square root, so it'll all be in terms of rho G in the end. And so I just cannot worry about that. Squared. All right. Now your issue was, is this pointing in the correct direction? That's the question. All right. I don't know, but let's figure out the angle and see what happens. So tan of this angle will be that divided by that. Damn it, 5.25 L, which I cannot figure out, but I'm just going to leave it like that. No, just a second. Which is exactly 1/3 of L. So when I did this divided by this, I got 0.33333333, which is 1/3. So, yep. Oh, for the sake of Frel, David. Thank you. No, the L was on the 5, wasn't it? Oh, so that's not going to come out to anything fun. But it'll be different for different L's. Okay, so, yep. Yeah. So I'm just going to say, I'm going to repeat what you've said. I could find, I'm struggling. Did you want to ask me something back there in the corner? No? Okay. These guys are figuring it out. If I knew what this angle was, I could figure out this L because I could use tan or something to figure that out. And if I knew what L was, I could figure out this angle too, or vice versa. And it looks to me like the longer this L is, the bigger this force is going to be. Yeah. Because the more of it will be sitting directly under the water, pushing it down. Ah, so in our original one, the L is 0, and so that sort of just cancelled out. Cool, okay. So I want to figure out what this angle here is based on the L. So I had this diagram. There's an L here. This total was 5, which means this bit is 3. Which means, are you ready? This angle here, tan of that angle, is L on 3. Because it's opposite over adjacent. And that angle, if I draw something here, pointing inwards, that angle will be here, which is the exact angle I drew here. So the two angles work out to be the same either way. So it turns out that if you do this process with the dividing into the horizontal bit and the weight of the water, the force will be guaranteed to be pointing in the correct direction. So you don't have to worry about it. Yay. Okay. Yay, maths, for solving the problem for us. So, how are people feeling? Do you feel like you've covered the what ifs that you're interested in with hydrostatic force? I'm very happy with you doing that what if because it meant that we had to combine both of these at the same time, which I kind of liked. Yeah. All right, I'm going to try and put these in the correct order. Right, so we've got about 40 minutes to talk about internal forces. So there was a one in the assignments that I don't want to do because it was in the assignments and they may want to recycle them next year and this video will be there next year. But I'll show a brief picture of it, but I won't solve it. That one. I'll just share it to the Zoom as well. This one was one of the assignment questions. I don't think they mind if I share it early. Just won't tell them. But I don't want to actually do it because next year's students will have a solution for them. But I'll find something that's similar-ish and see what we can do. Okay, this may turn to crap, but I'm going to give it a go. Luckily, I have an actual work solution to check on just in case. I don't know if this is the correct drawing here, but these are affixed to the wall properly, like bolted in. Okay. Find the internal forces at point E. It's not attached to the wall. There's a wall here. Yeah. Just going to read the solution I've got here. Okay. Right. So there's a lot going on here. There is a force pulling down here. These two are connected together, and these are connected here, and these are connected here. I presume they are able to rotate, I think. Not really sure. Not really 100% sure what the hell is going on actually, but we're just gonna run with it. So this entire object has one force pulling down on it, and so these two spots here are going to have to pull upwards in order to cancel that out. That's definitely true. I'm good with that. So whatever the reaction forces are, the vertical reaction forces at these spots, they're going to have to cancel out this 600 newtons. And bolts. Bolted to the wall. Oh, I don't know how to draw it. I was just copying the picture that was here. So can I just check something? Sorry. No, it was an actual drawing in beautiful silver, but I'm pretty sure it matches with the way this picture works. These things, they're not rollers. They're proper attachments that can provide forces in multiple directions, right? So there's forces there's extra forces here too, right? Oh crap, just a second. Too many screens. There should be reaction forces at both of these places, in both directions. Except these are going to be 0 anyway because there's nothing pulling it in that direction. Like when you look at the entire object, the reaction at A vertically and the reaction at B vertically because when you look at for the entire frame, we know that the sum of the horizontal forces will be the reaction at B and the reaction at AX, sorry. And they have to add to 0. Oh, so maybe, oh, they're allowed to be, but one of them's the opposite way to the other. Nice. So they look like they're pointing this way, but one of them is possibly negative. Got it. Interesting. Oh, I am going to move, just give me a minute. I'm going to have to cut it at E eventually. I just want to, oh, you mean method of each thing. Yeah, just, you might, I don't know what statically indeterminate means. I'm a mathematician. That's a physics word. What does that mean? Okay. Oh, that's a trust thing, is it? It must be possible to figure out what we need to do the bending moments and crap though. So just my understanding is that I would normally look at the entire frame to figure out what the reactions are doing at certain spots. But if I did the moment around this though, yes, yes, I can do it. So the forces in the x direction and the forces in the y direction have to add up, and the moments around any point you want have to add up to 0. And this point has 3 forces pointing at it or away from it, and so they're not going to come into the moments. Only this one and this one are going to come into the moments around that point. So I'm going to do the moments around A. So the moments around A, I've got the reaction force at B of it time in the x direction times a distance of 2. And that's going this way, so that's positive. And I've got the 600 newtons at a distance of 1 away, because it's 1 perpendicular to the 600 newtons. And that's negative. And so the RBX, 2RBX is 600, and so RBX must be 300. Cool. And so that's actually a proper positive one. This arrow is pointing in the correct direction, which means that this arrow is pointing the other way. It goes that way there. And then there's not enough information to figure out RAY and RBY. And as you say, there's too many unknowns. But that's fine. It may be enough to do what I want to do. Okay. All right. So now I could pull just on individual pieces of this thing, like just look at this thing, maybe? Is that what you're talking about with method of, I don't know. So this thing has a piece of force pulling from this thing and a piece of, oh crap. Cool. So this, based on this diagram, which is just the member AC, which maybe I should have started with, says that based on the horizontal forces, says that this force here, which I don't know what it is, it's just the piece that's provided by that bit just there. Just F. Tell me. Yeah, this is the force of this member pulling on this thing. But it does have to match this one. And then yay! So I figured out RAY after all. Awesome, which means that RBY has to be 0 because these two, no, it has to be minus 600, it has to be pulling down. No. No. Tell me more. Well, these people in the textbook think that it's possible. So, cool. So just let me see what I did. I looked at the entire thing and I got some information about what this one was from that. And then I looked at just this piece and I had to add an extra force. And so now I've got this one, I know what all of these bits are. So I'm just going to redraw the diagram so I know properly what's going on. This is 300 this way. This one was 300 this way because it was minus 300. And here's my point E. So I've managed to just pull out one piece of this object, which is here, and figure out what all the forces are that are going on inside this member of the frame. Is that the right word, member? Is that what they call them? And then, should have picked an easier one. Yeah. I just want to check something. If I do with the moments around this point, then this is 1 away, and this is 1 away too. So shouldn't that mean that those two are the same, and so it's not 600? Oh, for the sake of Frel. Give me a moment. They've done. I may give up on this and do a different problem because their solution doesn't make sense to me because they haven't resolved these forces. They've done them as an angled force. Yeah. I'll sign 45. Nope, it is 600. I was right. There are just extra moments floating around. I think there's a moment in this member, this corner caused by this thing pulling as well. So, okay. While you're at it, Engineering Mechanics Statics by R.C. Hibbler, in case you were wondering. Okay, so then what they've done is to find the internal forces at E, they've pulled out just this bit. I'm very confused. I think I did something wrong earlier. Okay. I may give up and just do the one that's in the assignment because I know how to do that one. What they did is they started out by pulling this apart into its separate pieces, this bit and this bit. And they said that this thing should have forces pulling diagonally this way. And this thing, because it's straight, should have forces pushing inwards this way. And then this is what's going on at this spot here. Oh, there's another reaction. Okay. I know what I did wrong. There's a reaction here too of this, because this thing's pulling back on it, this thing's pulling up on it here. Oh, okay. I choose to admit defeat and tell you what they did. they went at this because this is a member that pulls on things, it's going to have equal forces at both ends because it's sitting still. And because it's a straight line with rotating pins at these spots, it can only have forces inwards. I think that's what they've done. Yeah, okay. Should have picked something that wasn't quite so intense. I'm sorry. We'll try again with something that's actually in the course notes. This one I can do. Let's try again. Thanks for bearing with me. This is how to possibly just pass your exam if you didn't go to any classes, because I didn't. Okay. So this one has do they normally draw it with, how do they draw a thing where it's a roller? Like that? This is a bridge. There's a cliff. There's a bit that the bridge is standing on. I don't know, and it's probably some sort of suspend. I don't know. Who knows? It's got a motor maybe that. Okay, so we have I didn't give myself enough space. Here, there is a 2.5 kilonewton load, and it's 3 meters along. And then this is 4 meters, and at the position of 2 meters, there is a point which they have called C, and they've called this point A. And then they've got 4 meters this way, cantilevered out the end, and at a position 3 meters along here, they've got a point which they have labelled D, and this one's called B, and this one's called E. And a bit fuzzy. The shear force and the moments at the points C and D they're asking for. I may just do one of them. Cool. This one's a little less stressful. So there should be, so this being a roller means it can only produce upwards reaction. Is that how it works? Because it's on wheels that they can't push this way. Okay, and this one being a proper, whatever this is called, pin? What? Pin? Means it can produce reactions in both directions. That's the idea. And so I have There's reactions in both directions here, and there's a reaction here. Is that all the forces that are acting on this thing, do you think? And so there's not going to actually be a reaction here because there's no horizontal forces to counteract it. So this one here doesn't actually exist. We can just skip that bit. So I'll call this the reaction at A and the reaction at B. So even though it's possible to provide a reaction at this spot, it's not, there isn't one. So I'm thinking about the entire object at the moment. And so if I do the upwards, I've already used the sum of the forces in the x direction being 0 because that means that there's no horizontal reaction at B. The sum of the forces in the vertical direction isn't going to tell me what both RA and RB is because I'll have that these two added together has to be equal to 2.5 kilonewtons. So I might skip that one. But if I did the moment around one of them, I could figure out the other. So moments around A, say. So what have we got? We've got, that one doesn't count. We've got 2.5 kilonewtons at a distance of 3, according to the original diagram. And that is going, that's negative, because it's pointing downwards. And then I've got whatever RB is at a distance of 3 plus 4, so 7. And so RB times 7 is 2.5 times 3. And so RB is whatever 2.5 times 3 over 7 is, which is what calculators are for. And then RB, I could do the moments around B to get RA as well if I want, or I could use the sum of the forces in the vertical direction. That would also tell me what RA is as well. So I've got that RA minus 2.5 plus RB should be 0. And so therefore RB should be 2.5 minus RA. Sorry, RA should be 2.5 minus RB. I probably didn't need to figure out both of them, but you know, here I am. Okay. I have a feeling that I only needed one of these to actually do the bending moment stuff, because maybe, not sure. Okay, so I know what all the forces are that are acting on this thing, and then to do the internal forces and moments at a particular location, I need to cut my object into two pieces, one on one side and one on the other. That's my understanding of how it goes. And so I can take my object. I got the point C. The RA is whatever RA is. And I can cut this into two pieces and it doesn't much matter which piece it is. I decide to cut it here and cross that bit out, because it's only got one force in this bit, and I've already figured that bit out. Is that a good plan, do you think? Okay. And so at the edges of this, so here we go. This thing all by itself, if we're talking about a shear force, then we have one that's going, does it go up on the left and down on the right, or is it the other way around? I can never remember. So they're my shear forces. And then my bending moments go smiley, right? There isn't one there, but like that's the idea, isn't it? Is that right? It's not actually here though, that orange one, which I can't cross out. But so I just put them here, don't I? I don't put them at this end, but that's the imagining, right? I imagine that there's one at both ends, which tells me that which is the correct direction for positive in this spot. Have I got that right? Okay, cool. Okay, and so I believe this is traditionally called V, and I'll just call it M, I guess, or did you call it BM? Sorry? BM? Okay. So now here we are at C, all this crap is gone, and now I can just look at what's going on inside this member. And so the V has to match with this, and it actually has to be going the other way. So it's actually bending the downwards rather than upwards. So we've got V so because I've drawn it to be up, but it's minus, it's actually pointing down, which means the thing's actually bending this way. Yeah. Maybe, or the other way? Not bending at all, it's shearing. What does that mean? I don't know. I don't know what that. Oh, sorry. I was all confused because I thought we were over here, but we're here. Of course it's going downwards because the load is right next to it. Okay. So this V would have to go down because the load just over here is pushing it down. And whatever. I forget what the shearing does. But that's what that does. And then the sum of the moments at C. And I have to do the moments at C because this moment only exists at C. So I can't do it at any other spot. What was this distance? 2 meters. So that's going the other way as well. But that makes sense too, because this piece of the beam should be bending down. Oh, crap. I always do this wrong. Oh, no, that makes sense. If this side's bending downwards, this side should be bending that way, and that's why it's that way. That's why it's a frowny face, which is a negative moment, because I've done it on this side of the thing instead of on the other side where it would have come out to be positive. They would have both been positive then. Does that make, does that work? If I had cut it this way, they would have both come out to be plus, because they should be the opposite directions on either, on the inside, I think. I don't know the physics. All I know is the maths. So, but I'm pretty sure that if they asked for the magnitude of them, this would be the correct answer. Yep. Oh, of course, could be positive. So I should have been confused because my answer was wrong. Sweet. Should have trusted my instincts better. This is my problem. So you're saying, yes, that goes over there, it'll be plus, switch them around. I shouldn't have done two things at once. That's my problem. Okay. the world is making slightly more sense now. Okay. Now, if I was at D, then I've got this whole thing going on, and there's D. And so if I cross this bit out, then there's no other forces in this spot at all. And so there's no shear forces or bending moments over here at D. Okay. Which makes sense, I guess. There's nothing sitting on the beam over that end. It will just be flopping around the way it likes to. I don't know if your lecturer has any more times to meet you with. Did they do all that last week? This would be a really good, very specific question to ask someone who runs this course, now that we've gotten to the point of the Maths Learning Centre knowing how it works. So the other thing, so the one that was in the assignment was difficult because it had a diagonal force pulling as well, but that could be resolved into pieces, and you still need to do it for the whole object before you do it for the individual bits. So I think the one that made the example that I picked in the notes difficult is because it was made of several objects bolted together, whereas this one is just a single object. And so the one in the note in the assignment was a single object too. So I should have tried to find one that had a single object with stuff pulling in different directions. Sorry about that. So I just have one more thing to look at. I believe this one's from one of the practice exam / quiz things. And I know I'm supposed to finish at 4, but I'm on a roll. So this is the diagram. I think there are lots of ways that we could attack this. So 2 ways to attack this would be to replace this distributed load with a single load. But I don't think that's the vibe that you yours normally do. You normally draw one of these diagrams of the forces going up and down and stuff. But I'm just going to check at what the actual questions were. Determine the horizontal and vertical reactions at B. Determine the reactions at C. Calculate the values of the internal shear forces in the beam at the points A, B, C, and D. And then also bending moments at those places. And the maximum value of the internal bending moment in the location at which that occurs. Okay. So for part C, the maximum value of a bending moment would be, I would need to know what the bending moment was at every moment, at every position, in order to know what the maximum was. But I think, doesn't the maximum value of the bending moment happen at the position where the shear force is 0? Is that right? So I either have to know what the shear force is at every location, or I have to know what the bending moment is at every location. But I do know that the shear force equals 0 at the maximum of the bending moment. So if I could draw a diagram of what the shear force looks like, I may have a chance of doing this without actually figuring out a formula for the shear force. So there's this magical shear force diagram, right? Where here's A, here's B, here's C, and here's D. And then you just follow the forces in the direction that they're pointing. We follow this down 5, and then the shear force has to go the other way. Or do I do it up? I can never remember which way around it is. Just a second. Oh, I'd have to figure out the reaction forces to do that first, wouldn't I? Sweet, okay. I'll come back to that. It's like watching one of those. Have you ever seen those things online where someone does the recipe and for like a Cookie Monster cake and they say nailed it? Sorry, this is where I am. So I have to figure out where the reaction forces are. So I have no choice but to figure out how to do that. So there would be a reaction at B in 2 different directions and a reaction at C because that was a roller here and this one was a pin here, so it has those things there. So there are no horizontal forces acting, and so this one must be 0. So RBX must be 0 because the sum of the forces in the x direction is 0. Because there aren't any other forces acting horizontally, so we're good with that. All right. And then this reaction, these 2 reactions have to add up to the whole of all of this. My instinct would be to do what I did with the fluid pressure and replace this whole thing with a single force. That would be my instinct. Does that sound like a good plan? Okay. That's a rectangle. It's 8 long because this was 6 here and this was 2 here. And it's 5 kilonewtons per meter high. And so the total force of the distributed loading is 8 by 5, which is 40 kilonewtons. And its location is halfway. And so that would be half of the 8, which is 4 of the way from B. What's that? I'll add this on here. Yeah. I was saying it's 4 away from B, so it's 6 away from A. Is that what you were saying? Yeah. And yeah, it's halfway along the rectangle. So my new diagram is now I should really try and draw it slightly more accurately so I don't get so surprised when things turn out the way they do. This one's 5 kilonewtons. And then this was 2 meters. And then 4 meters away from B, that's now 40 kilonewtons. And then another 2 meters. And then another 2 meters here. Oh, and then there's the reaction at C, right? There's a reaction here and a reaction here. Okay. So I've replaced the distributed loading with a single load at a specific location. It should be halfway along the bit where the distributed load was. And it was 8 along here, so it's 4 there. And so I should be able to figure out one of these from a moment. So if I do the sum of the moments around B, then I've got a 5 kilonewtons acting at 2 meters away and causing a positive rotation. And I've got 40 kilonewtons acting at 4 meters away and causing a negative rotation. And I've got the reaction at C acting at 2 plus 4 plus another 2, so 8 meters away and going positively. Cool. So I've got 10 minus 80. That is so not 10 minus 80. 10 minus 160. I'm just going to write them down. 10. (160) minus 10, which is 150. And so RC is 150 divided by 8, which is whatever it is. And then the sum of the forces in the y direction I was doing the reactions. Oh, damn it. I got confused because one of them was at A. 6. Thank you. 6. Because the first one went to A, I started doing everything from A. But then I did this one. Oh, thank you. Sometimes I wish I had a little mistake fairy in my exam with me. Okay, so it'll be divided by 6, which is a nice clean number. So I've got minus 5 over here, plus the reaction at B, and then a minus 40, and plus the reaction at C, which is 25, and that's supposed to be 0. Okay, so now I have all the bits. I can put them back in my diagram now. Damn it, I just actually went to all the effort of finding what this was. See, this is T, this is A, 2 meters, 4 meters, 2 meters, 2 meters. Okay. Sweet. I really should, I'm going to lose that if I put it in the wrong spot. Okay. Okay. And so I've forgotten what the goal was. Oh, to figure out the reactions. I did that. Okay. So now I've got the reaction forces. I'm going to color code them because they were reactions. Okay. So now I've lost track of what my goal was now. I found the reactions. That is one of the questions in the exam. Shear forces. Okay. Cool. Okay. Now I can draw my shear force diagram. Awesome. So there's actually, I can put this 40 kilonewtons distributed loading back again as a distributed loading to draw my shear force diagram. Still there. So if I'm going to draw my shear force diagram, there's A, there's B, there's C, and there's D. Pretty sure this is where I want to just check the notes. Not that. Yep, okay. I'm going to follow the forces in the direction they go. It's going to be 5 kilonewtons down here. That's this force. And that's going to stay exactly as it is all the way along here because there's no other forces to counteract it with. And then it's going to start having it's going to have this reaction force of 20 kilonewtons, which is going to go up to here. So that's going to be 15 now. And then it's going to start having this downward distributed loading, which is going to add a little bit extra as I go along. And by the time I get to D, it will be down 40 from where it was there. I need more space or make my diagram shorter. So it's down 5, up 15, so up 20, which is now 15 up. And then it's going to go down 40 by the time it gets to here, except it's going to go up again in the middle. Sweet, okay, that's okay. I can deal with it. So down 40 from here would be down 15 and down another 25. That's down 40, and it would be going in that direction, that slope. But then the 25 would make it go up again from here, and then it would copy that same slope and end up here, like that. So this bit here, this line, is what the distributed loading would look like if the reaction at C wasn't there. It would start at 15 and it would keep adding a little bit extra downwards until it got all the way down to minus 40 from where it started. So this triangle here is 40 that way. And so this is, and it doesn't technically actually touch the axis here. That's a dotted line. It doesn't technically touch the axis here either. That's a dotted line. And so it's this point that I'm interested in. That is where the bending moment is the maximum, because that's where the shear force is 0, whatever that point is. So this slope here, it goes across 8 and down 40, which is minus 5. which means if it goes down 15, it's going to have to go across 3 to get a slope of -5. So this is 3 here. And so therefore, the position is 5. 3 here and 2 there and 3 there. I would like someone to ask me what's going on here, or to say something about how they feel about what I did. Thank you. I'm going to say something about that distributed loading. If that distributed loading was all by itself and there was nothing else going on, then it would start here at B and it would finish here at D and it would go down like that. That would be the bending moment. If all, not the bending moment, if that distributed loading was all there was, it would produce this thing. And the slope is 5. I actually knew the slope was 5 because every meter goes down 5. Every meter adds an extra 5 kilonewtons. That's what the distributed loading was. It was 5 kilonewtons per meter. And so I didn't even need to know the 40. I know that for every 1 across, it goes down 5. So for every meter across, it goes down 5 kilonewtons because that's what this means. 5 kilonewtons down for every meter across. So I could have done that much more easily than I did before. I'm going to redo my diagram. We went down 5 and then that didn't change until we got to 2. And then there was an up 15, so an up 20, which means this is 15 here. And then we go down at a slope of 5. So every 1 across is down 5, so it'll go down 5 and down 5 and down 5 again, and then it will hit the line. And then it will keep going down 5 for every 1 across until it gets to C. So we were at B here, 1, 2, 3, 4, 5, 6 to get to C. Here we are at C, and then we'll go up the 25 that's at C. So we were at -5, -10, -15, 5, 10, 15, 20, 20. That's now 10. And then we go down 2 lots of 5 here because the distributed loading is still coming. And this is the point. And because the slope here is 5 down for every 1 across, this distance must be 3 because we went down 3 lots of 5. Right. So the position when V equals 0 is 3 from B, i.e. it's 5 from A. The bending moment is the integral of V, isn't it? Is that right? Well, yeah, because V being 0, telling you that the bending moment is at its maximum means that the V must be the derivative of bending moment. So the bending moment at this point should be the area of this. Yes! So the area so far is, let's see, it's 5 down and 2 wide. So it's 5 down and 2 wide here. And then it's and then plus the area of this triangle, which is 15 high and 3 wide. Pretty sure. I don't know whether it's plus or minus though, I'm sorry. No, it must be plus. Let me just check the notes. What is W? Oh no, I know what that is. W is the distributed loading. Must be here somewhere. I'm looking for a derivative. Here it is. V is dm on dx, and that must mean that the integral of V is m, and so that's the area. Okay, cool. I'm all good. Sweet. All right. That was cool. So I didn't actually have to actually calculate any integrals or anything. I could do it from the diagram with the areas. That's nice. I haven't actually answered the problem of finding the bending moments at the other points, but it's really time to stop and go home. Yeah, thank you so much for letting me muddle that through. I'm very happy with that bit. And I'm very happy with the fluid pressure stuff. That was excellent for people who helped me. And thanks for everyone for helping, for telling me pieces of information about how the lecturer does things. That's useful stuff. And I'll stop the recording there.